Hello, welcome to AS Mechanics in 30 minutes. I'm Tony Debling. I'm going to talk you through the key points you need to understand for your examination. Let's start with the formula booklet. It will include only the suvat formulas for the AS exam. Let's take a closer look at these. We have V equals U plus AT, where U is the initial velocity, V is the velocity at time t. This really is a definition of acceleration. After 1 second, an acceleration of A means the velocity will increase by A. So after t seconds, with constant acceleration, it will increase by AT. Also, you'll see that the gradient of the velocity time graph is the same as the acceleration. Let's look at the last formula. S equals a half U plus V times t. This is the average speed, a half U plus V, multiplied by the time. That gives us the distance. This is also the area underneath the velocity time graph. I'd like just to highlight the V squared equals U squared plus 2AS formula, just to note that this is the only formula that doesn't include t. Let's look at a typical suvat problem. The train travels along a straight horizontal track between two stations A and B. In a model of the motion, the train starts from rest at A and moves with constant acceleration of 0.3 meters per second for 80 seconds. So the velocity will be 80 times 0.3. We could use the suvat formula, V equals U plus AT, so V would be 0.3 times 80 equal to 24 meters per second. The train then moves at a constant velocity before it moves with a constant deceleration of 0.5 meters per second, coming to rest at B. We've got to find the time for which the train is decelerating. So similarly, dividing 24 by 0.5 gives us a time of 48 seconds. We then have to sketch a velocity time graph. So we have the velocity on the vertical axis, the time on the horizontal axis. Here we have a period of initial acceleration for 80 seconds, reaching a velocity of 24. We have a period of constant velocity, 24, and then finally 48 seconds decelerating at 0.5 meters per second. We're told the total distance between the two stations is 4,800 meters. So using this graph, we take the area under the graph to be the distance travelled. So this is a trapezium. So we want to half the average of the two parallel sides, so that's t plus 80 plus t plus 48 times 24, the perpendicular height, and that will equal 4,800. We solve that for t and we get t is 136, and therefore the total time to travel from A to B will be 80 plus 136 plus 48 equals 264 seconds. We're asked to suggest an improvement for the modelling that could be made, and the main thing with the velocity time graphs is that they're very angular, and so a more accurate model would have a more gradual build-up of acceleration and smoother transitions between the acceleration and the uniform velocity. Let's look at a second question on kinematics. We're told a cyclist is moving along a straight horizontal road and passes through point A. 5 seconds later, at the instant when she's moving with speed 10 meters per second, she passes the point B. She moves with a constant acceleration from A to B. Let's call that little a. We don't happen to know the velocity when she's passing through A, but we're told that AB is 40 metres. We have to find the acceleration of the cyclist as she moves from A to B. So here we're going to use the suvat formula, S equals Vt minus a half AT squared. We're going to substitute S is 40, T is 5 and V is 10 to get this equation, from which we derive that A is 0.8 metres per second. We can work out U, the velocity at A. We know V is 10, we don't know U, 0.8 times 5. From this we can calculate that the initial velocity was 6 metres per second. The second part of the question asks us the time that it takes her to travel from A to the midpoint of AB, that is a distance of 20 metres. So here we use S equals ut plus a half AT squared. So we know the distance is S, U is 6, and the acceleration is constant at 0.8. Here we get a quadratic in T, which has a positive and a negative root. We take the positive root, which is 2.81 seconds. Here we use the formula to calculate that root. Now we look at the motion of a particle under gravity. Very common question in your AS papers. A man throws a ball into the air so that at the instant when the ball leaves his hand, it is 2 metres above the ground and is moving vertically upwards at a speed of 9 metres per second. It will have a constant acceleration downwards under gravity, which we're told to take as 10 metres per second. And then the ball hits the ground big T seconds after leaving the man's hand. We're going to use the model to find a value of T. Usually with these questions, it's best to measure everything from the point of projection so that this becomes the origin of your coordinates. And you need to take care to get the signs of the quantities correct and to measure the displacement from the point of projection. So here we're going to use the formula S equals ut plus a half AT squared. S is going to be minus 2. So we want to find out the time at which the displacement is minus 2. That's 2 metres below the point of projection. We know the initial velocity is 9, measured in the positive upward direction. We know gravity is minus 10, as it's going in the negative direction. So we get this quadratic. We rearrange it, we solve it. We have one positive root, and that is big T equal 2. There are other common questions, like what is the maximum height that the projection reaches above the ground? So again, let's draw a picture. We know at the top of the projection V equals 0. So here we use V squared equals U squared plus 2AS. So 0 squared equals 9 squared. 2 times minus 10, the acceleration due to gravity, times the height above the point of projection. So here we get h equals 4.05. To calculate the height above the ground, we need to add 2 to give us 6.05 metres. Another common question, for how long is the particle more than 5 metres above the ground? Let's take a look at this scenario. Here, 5 metres above the ground, S equals 3 metres above the point of projection. S equals ut plus a half AT squared. We get 3 equals 9t minus 5t squared. We get this quadratic. We solve it using the quadratic formula. Here we'll note that the 0.9 is the time it takes from the point of projection to its maximum height. And the two roots are 0.9 minus 0.458 for the first time it reaches 5 metres, and then 0.9 plus 0.458, that's on its way down. So the time it spends above the 5 meters is going to be twice the 0.458, which is 0.916 seconds. Now let's look at an example of a vectors question. A boat travels from A to B and then from B to C. The displacement from A to B is minus 28I plus 80J. The displacement from B to C is 130I plus 15J, and we're asked to find the total distance the boat travelled. Notice here an important difference between displacement and distance. We're now looking at the total distance travelled, so we want the length AB, which is simply the magnitude of the vector minus 28I plus 80J. So here we use Pythagoras. And similarly, for the magnitude of BC, we use Pythagoras. The distance travelled will be the sum of these two magnitudes, 215.62. We're asked to find the angle the vector AC makes with the unit vector I. So first we calculate the vector AC, which is simply the sum of AB and BC. That's 102I plus 95J. Then we have a simple piece of trigonometry where the angle alpha that AC makes with the unit vector I, we can see that the tan of alpha will be 95 divided by 102. So alpha is tan to the minus 1, 95 over 102, which is 42.96. This question could equally have been a problem about two forces, F1 equal to minus 28I plus 80J, F2 equal to 130I plus 15J. We may have been asked to find the magnitude and the direction of the resultant force. So here we'd simply find the magnitude and direction of the combined vector AC. Let's look at a problem involving connected particles. We've got two small balls P and Q with masses 2m and km, where k is less than 2. So add their weights onto the diagram. As k is less than 2, P will fall and Q will rise. They're attached to the ends of a string passing over a fixed pulley, which later on we're told is small and smooth. So as it's a smooth pulley, the tension will be the same both sides, so we can mark on the tensions T. We're also told that the systems are released from rest, and in the subsequent motion P moves downwards with an acceleration of 5g over 7. So we're first asked to find in terms of m and g the tension in the string. So we apply F equals ma at P. There's a mass of 2m. The forces acting on it are 2mg downwards minus t upwards, and that is causing the mass of 2m to accelerate downwards with an acceleration of 5g over 7. So we can calculate t equals 4mg over 7. We're then asked to explain why q also has an acceleration of magnitude 5g over 7. This is because the string is inextensible. So the displacement of q up equals the displacement of p down. The velocity of q up equals the velocity of p down at any point in time. And similarly, the acceleration of q equals the acceleration of p down. Then we're asked to find the value of k, so we apply F equals ma also at q. So here the net force is T up minus kmg down, and this is causing a mass of km to accelerate at 5g over 7. We rearrange this and we find k equals a third. Identify a limitation of the model. Well, it's unlikely that the pulley is perfectly smooth, and this is going to provide some resistance to motion. Let's look at another connected particle problem. A box of mass 0.8 kilograms rests on a rough horizontal surface and is attached to one end of a light inextensible string. The string passes over a smooth pulley at the edge of the table. The other end of the string is attached to a sphere B of mass 1.2 kilograms. We have our two masses, we add the weights to the diagram, we add the tensions to the string, we add the reaction from the table, and we add the friction F. The system is released from rest with the string taut. We're told that after release, B descends a distance of 0.9 meters in 0.8 seconds. B will start from rest, so U equals 0. The distance that it travels is 0.9 meters and the time it takes is 0.8 seconds. The acceleration is A. So we use S equals ut plus a half at squared. We get 0.9 equals 0 times 0.8 plus a half a times 0.8 squared. From this we calculate that A equals 2.81 meters per second. Next we apply F equals ma for the sphere B. The net force is 1.2 g minus t, and that's causing the mass of 1.2 kilograms to accelerate with the acceleration A, which we've calculated to be 2.81 meters per second. From this we can calculate the tension as 8.4 newtons. To calculate the value of F, we apply F equals ma to the block A. Here we have the tension, 8.4 newtons, minus the friction F. That's going to equal ma 0.8 times the acceleration 2.81, from which we can calculate that the value of F is 6.15 newtons. Let's look at a lift problem. A woman travels in a lift. The mass of the woman is 50 kilograms and the mass of the lift is 950 kilograms. It's being raised vertically by a vertical cable which is attached to the top of the lift. The lift is moving upwards and has a constant deceleration of 2 meters per second. By modelling the cable as being light and inextensible, find the tension in the cable. So let's add the woman inside the lift with her weight of 50 g. In addition, there's an equal and opposite reaction. The lift is pushing the woman up with a reaction of R. The woman is pushing the lift down with a reaction of R. We're told that the deceleration is 2 meters per second squared and it's moving upwards. So this is equivalent to an acceleration downwards of 2 meters per second. Both the woman and the lift will be accelerating at the same rate. We apply F equals ma for the lift. The forces acting on the lift are, there's a reaction pulling it downwards, there's a tension pulling it upwards, there's the weight of the lift pulling it downwards, and that's causing the mass of 950 kilograms to accelerate at the rate of 2 meters per second. For the woman, we apply F equals ma. The forces acting on the woman are the weight of 50 g minus the reaction of the lift on the woman, which is R, and the woman is accelerating downwards at a rate of 2 meters per second. So this equals 50 times 2. F equals ma for the system is obtained by adding these two equations together, where the internal reaction forces cancel. So here, minus T plus 50G plus 950G is going to equal 950 plus 50 times 2. From this we can calculate the tension as 1000 times G minus 2. To calculate the magnitude of the force exerted on the woman by the floor of the lift, this is this reactive force R, we simply rearrange F equals ma for the woman to get R equals 50 times g minus 2. Our final question is about kinematics in a situation where we have variable acceleration. A particle P moves along the x-axis at time t seconds, t greater than 0. The displacement x meters of P from the origin is given by x equals a half t squared times t squared minus 2t plus 1. Firstly, we have to find the times when P is instantaneously at rest. This means when the velocity is 0. Given the displacement x, we can calculate the velocity by differentiating the displacement with respect to time. So we get v equals dx by dt equals 2t cubed minus 3t squared plus t, which we can factorise to give t times 2t minus 1 times t minus 1. So this equals 0 when t equals 0, 0.5 and 1. Let's just draw a velocity time graph. We can see it will be a cubic. It crosses the t-axis where t equals 0, 0.5 and 1. So what happens here, between 0 and 0.5 seconds, the velocity is positive. So it's moving away from the origin in the positive direction. Between 0.5 and 1 seconds, the velocity is negative. So it's actually moving back towards the origin. And then when t equals 1, the velocity becomes positive again, so it moves back away from the origin. We're asked to find the total distance travelled by P in this time interval, 0 less than or equal to t less than or equal to 2. Let's look at the displacement at these various points in time. So between t equals 0 and t equals 0.5, there's a positive velocity and it's travelled a distance of 1 over 32 away from the origin. Between t equals 0.5 and t equals 1, the velocity is negative and it's travelled a distance 1 over 32 back to the origin. And then between t equals 1 and t equals 2, it's travelled a distance of 2 away from the origin. So the total distance travelled will be 1 over 32 out, 1 over 32 back, and then 2 out, making a total distance of 2.0625. To show that P will never move along the negative axis, we can rearrange the formula for x. Say x equals a half t squared times t minus 1 squared, which will be positive for all t, and therefore x will never be negative. To calculate the acceleration, were we asked to do so, we'd differentiate the velocity and we get a equal to 6t squared minus 6t plus 1. That's all, folks. I hope you find it useful and good luck in your examination.